Thank you very much. Thank you very much, Adrian, for the introduction, and I'd like to thank the organisers for this opportunity. So if I can try and share the screen now, see if this works as good as it did in the practice. Okay, so I think that's right. So as Adrian said, I'm going to be talking a bit about some work that we've just got published in a Faraday discussion on CO2 utilisation. So in fact, this citation may be a little bit out of date. I saw my email today that we've just got page numbers for this. So I apologize to anyone who was at this meeting, because there's a lot of this talk is going to kind of rehash what I said there. But I hope it's still quite interesting. So this work really kind of built off a very successful big EPSRC call for CO2 utilization. So we are looking at using kind of CO2 and water as feedstocks to make fine chemicals. So I mean, this was a big consortium of some very good experimentalists based at UCL and based at Manchester. So the bit that was really focused on Cardiff was looking at the thermal catalyzation of CO2, the thermal reduction using carbide materials. And so I'm actually going to talk in the first couple of slides a little bit about some work from this previous consortium. And later we decided that as part of work package 6 in the Catalysis hub to kind of go for a next generation catalyst that's kind of focused on some of the work that we did with the monocarbide systems and see if we can expand it into 2D ceramics. So I will spend the first couple of slides just talking about some of our previous work, and then I'll get on to the subject of this Faraday paper. So for some reason my slides aren't, oh, okay. I apologize for that. So in the previous work that we did, we were looking at the monocarbides. So for a lot of experimentalists, these can be formed via coking and considered quite a pain because they're very stable ceramics, but they have interesting catalytic properties that are actually quite similar to the precious metals, particularly palladium or platinum. So they can catalyze the reverse water gas shift reaction. They can catalyze some of the CO2 hydrogenation reactions. There's quite a few interesting reactions that these materials catalyze, and particularly the middle group transition metal carbides have some very interesting reactivity. So our targets were titanium, zirconium, vanadium, and niobium carbides. So all the early transition metal monocarbides. So when you cut these the surfaces for these materials, the low index surfaces have basically either metal carbon layers or mixed surfaces with both carbon and the metal. So the first thing we did was we looked at hydrogen loading. We looked to see where hydrogen bound on these surfaces. So when we look at the low index surfaces, we see that depending on the surface geometry, we get very different kind of absorption modes. So hydrogen, if there is a mixed phase, always prefers to absorb on the carbon, on top of the carbon sites. So we find this with the 001, so the 011 surface as shown here, and also the 001 surface, which is the dominant phase in these, in any nanoparticle you create from these. The energy, as I'll show you later, is for this surface is considerably lower than for the more reactive surface, which in this case is the metal terminated surface. So we actually find that when we have the carbon surface on top, we get a lot of reconstruction. So unfortunately, it's a metastable surface. So although I'll show it in this first slide, we don't consider the carbon terminated 1-on-1 plane after this, because whatever adsorbate you have, whether it's water, CO2, hydrogen, you get major reconstruction on that surface. So as I say here, we found that the dominant surface actually absorbs CO2, absorbs hydrogen the least strongly, which if you think about a hydrogenation reaction is actually what you want. You want it to hold on to the hydrogen, but you want the hydrogen to be there for further hydrogenation reactions, whereas the 1-on-1 surface is actually not so good for, it binds hydrogen very, very strongly. So it may well be that those protons, those hydrogens, are not available for further CO2 reduction. So then we looked at actual CO2 reduction on these surfaces, and we found that on both the 001 and the 011 surfaces, there was a significant barrier, about between 0.5 and 1 eV for CO2 reduction, for CO2 activation by transferring an electron from the conduction band into, well, in this case, it's the pi antibonding orbital. However, we found, which has been reported experimentally and other groups, that on the 1-on-1 metal terminated surface, this reaction is barrierless. These surfaces are very good at activating CO2 without a barrier. So we then had a look at water. So if you think of a post-combustion CO2 utilization, there's a very large percentage of a flue gas that will be that will have water as steam. So we thought we want to have a look, see what happens when water binds to the surface. So if you see, we're now looking at the low index plane, so for obviously the carbon terminated 1-on-1, and we see again that water binds the least strongly to the dominant surface. And actually we found that for both niobium and for the vanadium surfaces, we found that niobium and zirconium surfaces, we found that actually the if water was to absorb, it would really absorb in a as a hydrogen and hydroxyl. So we get this kind of active state, or we get endothermic absorption. That's what the star is there. So then we thought, okay, so what happens when we co-bind CO2 and water, which is what you find in the flue gas? So when we looked at this, so we decided to, this scheme here sees everything set to 0 with the CO2 bound on the surface. So there's for the dominant surface, there's a slight difference per surface, but we were really looking at what the effect of the added water absorption would be to the overall exothermicity. So we find that the reactant state, which is basically just consists of the CO2 that's bound, plus a hydrogen bond to the water through one of the hydrogens, is about the same, which makes sense because it's about the energy of one hydrogen bond. We find there's a very different transition states energy. So say with the vanadium, we've got 40.4 EV, and then we've got considerably higher for the titanium at 30 plus 0.67 EV. But we tend to get quite a good correlation between the transition state energy and the exothermicity of the overall reaction. We find that the energy added for this co-adsorption is between 0.5 EV and 1 EV. So we have quite a strong extra energy associated with the co-binding, which could help this process happen on the dominant surface, which is the one that we would expect to be most even if it's not most catalytically important, it's the most dominant in any nanoparticle. So this results were maybe slightly unsurprising, but there are also a good systematic kind of screening of what these materials do. So obviously we're not the only people who've been working on this, and there's been quite a lot of interest in the metal terminated 1,1 surfaces of these materials. So it's been known for quite a while that these are the ones that really are active at CO2 reduction, at least one electron reduction. So there has been quite a lot in the literature over the last, I'd say, 5 to 10 years over these 2D maxanes species. So basically, this is where the experimentalists are trying to extend the amount of the 1,1 plane that you see in the carbide materials. So usually they cap the growing surfaces with kind of either OH groups, fluorides, something to express more of the 1,1 metal plane. And then they adjust the thickness depending on the properties that they want. So these are really thin films. So when we had a look at this, we thought it's interesting to see how the similarities between this kind of material and two-dimensional silicon carbides, where one of the carbon layers is substituted for an interstitial layer of silicon. So these materials are well known to exhibit quite a strong preference for the basal 0001 plane with the metal terminated surface, which is quite nice for us because, I mean, these things are also formed through coking and through, and they're very, very stable. They're very stable and thermostable ceramics. So we thought, okay, so what's the properties that change with the silicon carbides through the maxenes, as these would be quite an interesting target that hasn't really had the same kind of focus as the maxenes have. So for this study, we decided that we needed quite a big slab to get away from any perpendicular dipole. So we decided to have a slab where we have 6 layers that are frozen, 6 layers that are allowed to react. So the 6 bottom layers really there to represent the bulk. And then we have 6 layers that are able to adapt to adsorbates and the reaction mechanism, and these kind of simulate the surface. We use PBE code. We did do some benchmarking previously with the related monocarbides, and we found that PBE really was as good as most of the other GGAs at kind of representing the properties of these materials. And we also, there's always a trade-off in DFT between the theory that you use and what you can do. So we really decided that we want to have a system that has a very large kind of slab model, and PBE is proven in related materials as well as the maxenes to actually work quite well at describing some properties. So some of the other parameters I list here, I know this is a general conference, so I'm not going to go through all of them, but I can obviously answer any questions that you have. So the first thing that we did was we looked at the stability of the different surface terminations. So as you can see, as you can imagine, with these slabs, there are only 2 possible slabs that you can get. One that has metal on the one surface and one that has silicon on the other, or metal and carbon slabs. So you can either cut between the metal and the carbon or between the metal and the silicon. And then obviously you decide which half the slab that you relax. So we found that the silicon and the carbon termination are really kind of metastable states. So this kind of goes back quite well to what we saw with the monocarbides, that when you have the carbon layer, that this is metastable. We found a very similar thing with the silicon carbides. So for the rest of the talk, I'm going to focus on the low energy structure, the lowest energy slabs, which had a silicon on the bottom and a metal termination on top, which is also what they see experimentally. The other thing that I would say is that just to prove how unstable these were, when we had any kind of oxidant in the top, we got major reconstruction with both the carbon and the silicon free layers. Okay, so when we looked at the properties of these materials, we saw that in actual fact, the basal 0001 plane of the silicon carbides was slightly higher in energy than what we saw with the monocarbides. So the surface energy is slightly lower with the monocarbides on the most dominant surface, but it's a lot lower in energy than what we see with the 111 metal terminated surface, which is the lowly that's not very well expressed on the monocarbides. And actually the main contributor to the difference in surface energy was the fact that we increased lattice parameters, or the total surface area per atom, when we have the interstitial silicon layers. So when we have the interstitial silicon layers, we expand the unit cell and we slightly increase the formation energy, but it's still very exothermic, but not so much as the monocarbides, which is also seen experimentally. But it shows you that these, as we see experimentally, these surfaces are expressed quite a lot in silicon carbides. When we look at the CO2 adsorption, we find very, very high activation energies or adsorption energies for the silicon carbide 0001 plane, the metal terminated plane, even higher than what we see with the normal 111 plane of the carbide. And this again is explained by the increase in the surface area. So that changes the binding sites. So the electronics of the surface is actually quite similar, but the distance between, so I can show you in the next slide, distance between the preferred binding site for the CO2, the preferred geometry, and the elongation of the CO bonds is greater with the larger surface energy materials. Let's see. So I do apologize that my screen keeps stopping. I think my computer's getting quite hot. But in any case, I will try again. So as this is a picture of the most favored adsorption sites on each silicon carbide surface. So what you see is that the adsorption sites, or the adsorption morphology that's the most favorable, depends quite strongly on the geometry of the surface. So these two adsorptions where the CO2 is sitting perpendicular, the carbons in the hollow site and the two oxygens are bound to adjacent carbons, or the one where it's more perpendicular. Both of these have been seen also in the metal terminated carbon surfaces, and they're very close in energy. But again, it depends very much on the local geometry of the surface. So we find that in fact we get more than 1 electron reduction in the CO2 on the titanium and zirconium carbons. So it's not just the electron that we put into the antibonding orbital. We also get some rehybridization and formation of some sigma bonds. So we get about 0.8 of an electron in zirconium, and we have about 0.7 in titanium, silicon carbide. We see about 1 eV reduction in vanadium and niobium case. So then we thought this was very good. It bodes quite well for the activity of these surfaces. And then we looked at hydrogen loading. So unfortunately, hydrogen loading on these surfaces is very, very exothermic. So we see that the actual change in exothermicity per hydrogen molecule, it does lose some of that exothermicity, but even at where all the holocytes are filled with kind of 8 hydrogens, we still have like the lowest, which is here at vanadium silicon carbide is 0.8 eV. So you can imagine if you look at a valence blonde plot where you have one side, the penalty being the hydrogen evolution or the hydrogen release, and the other side, the exothermicity of the product formation. The product formation has to be very, very exothermic to get over this barrier. So this is probably kinetically not feasible for, although hydrogen activation is very feasible, the actual having the hydrogens available for further reduction seems to be not so good on the pristine surfaces. But then we thought, okay, so these surfaces are very, very highly reactive. And in an oxidative environment, what would happen to these surfaces? So maybe the pristine surface is not what we want to be looking at. So first we started by looking at forming a water monolayer. So we tried a few different kind of hydrogen bonding networks and found the most stable conformations. So as you can see, this is energy in per water molecule for a surface monolayer of water. And what you see is that it's about 1 eV of energy that mostly comes from the preferred binding sites. So we get quite a big difference when we take the surface away and we look at the hydrogen bonding per water molecule. So we get a difference between 0.6 eV and 0.12 eV. And so obviously the 0.6 eV was the largest surface. So the water molecule sacrificed some of their hydrogen bonding network energy from having the preferred binding site of the surface, because that's where most of the energy came from. And so really we just saw that the surface, again, was very, very reactive, and the water monolayer's geometry was very much dependent on surface geometry. Okay, so then we moved on to see, okay, so what would happen in an oxidative environment? How strong would an oxygen monolayer be? And the answer is very. So we find energies, this is with reference to an oxygen molecule, not an oxygen atom. So these energies are extremely, extremely exothermic, up to about 4.6 EV per oxygen atom. Now, this actually correlates quite well to what they see with the MXenes, where it's about between 3 and 4. Obviously, again, it's that elongation of the lattice parameters that slightly destabilizes the surface, but they have a very similar activity to what the MXenes would see, where you'd expect them to be oxidized in these kind of environments. And then we kind of thought, okay, so what happens to the hydrogen availability on an oxidated surface? So we then decide to form hydroxyl atoms. So if you can imagine taking the energy of the hydroxyl away from the energy of the oxygen, these energies now look very good. So it's about 0.4 to like 0.05 EV for hydrogen adsorption. So you could imagine that these surfaces are going to be a lot better for hydrogenation reactions and have those that hydrogen evolution versus hydrogen dissociation being quite a dynamic process. So that's all I've got to say. I hope my time is quite, I think I'm quite good for the time. Let me just say that I hope that I've been able to show that these silicon carbides are quite an interesting class of materials, that really it's the incorporation of this silicon layer really has an effect on the reactivity by changing the surface energy, by changing the surface geometry to change activation. So we do predict from this kind of exploratory study that the pristine surfaces won't be so good for hydrogenation reactions, but hopefully in an oxidative environment, these surfaces will be better. So, I mean, there's some ongoing work with a student from UCL that's here as a visit, that where we're looking at using these hydroxylated surfaces as then the active surface for further CO2 reduction. So the results that aren't finished, but the initial results look quite promising. And I'd like to obviously thank the people who did help me a lot with the work, and obviously all the funding bodies and the people who gave me computational time. And I'd like to thank you guys for listening as well. Okay.
Thank you very much, Matt. Bang on time.
Excellent.
Can I just, so for everybody, please, if you have a question, please type it into the Q&A. I'll read it out. Then we don't have to shuffle people into being in and out of panelists, so it'll be more efficient. So first question is from Macon, who says, "Hi Matt, thanks for the great talk. During your initial," oh, Josie, do you want to, it says you would like to answer this question live. You want to make
No, it just means it goes away once you've answered it, so you don't have to.
Okay, fine, sorry, I'm showing my Zoom noviceness. So the question, Matt, from Macon is, "Hi Matt, thanks for the great talk. During your initial studies investigating the co-adsorption of CO2 and H2O, did you observe water deprotonation by the surface or by the activated CO2?
That's an excellent question. I think we saw there was quite a fast equilibrium between the water on the hydrogen on the water and the hydrogen on the CO2 in the co-bound state. Because if you can imagine, there's a very strong hydrogen bond between the water and the CO2, and that bond is very activated. So in fact, the hydrogen is between, I'd say, the oxygen of the CO2 and the oxygen of the water. So in the co-bound state, we found the energy both sides of that equilibrium were relatively the same, and the barrier was not so high. But we found that actually it depended, when it was just the water, whether we got intact water adsorption or this dissociative absorption was very much dependent on the position of the transition metal. So without CO2 there, it was very much dependent on whether you got group 4 or group 5 transition metal, to depending on whether you got the intact water absorption or the dissociative absorption. But yeah, to answer your question with the co-adsorption, there was an equilibrium. Very strong hydrogen, very activated hydrogen that could shuffle between the two oxygens quite effectively.
Thanks, Matt. So another question from Keith. It says, "What about the reaction product? Have you looked at the thermodynamics of product absorption or desorption?"
So this is something that the student at UCL is looking at the moment. So I can tell you that we have a relatively low barrier on the hydroxylated surface for formation. So we haven't, which is going now through to formic acid and various other products, but this is kind of really ongoing work. So it isn't in the paper that we looked at, which is more of an exploratory study, just looking at what the properties are of the surfaces and seeing how that can be related to what we know about related materials and their reactivity.
Great, thank you. And just to abuse my privilege as chair, so in terms of connecting with experiment, so you've shown these nice differences and potential and clear, strong surface effects. Would you be able to predict isotope effects, for isotopically substituted CO2, for example?
Yes, so I mean, this was really put out there as kind of a challenge for the experimentalists, that obviously their work is a lot harder than ours in terms of these kind of reaction mechanisms. But obviously from a theoretical point of view, kinetic isotope effects are kind of bread and butter for modeling. So we can certainly do the calculations, but there's not a lot of point until we've got some experimental evidence. So at the moment, these particular ceramics, because there's such a massive kind of chemical space for different kind of ceramics with these formula. So you can have aluminium in there, you have silicon in there. There's lots of different kind of carbide type materials. So there really hasn't been so much, as far as I'm aware, when I was originally writing this, experimental data, but it's certainly something we can model, and so it's certainly something that I would be very happy to model if there was something to model against.
Is there anything, I think, you know, it's always, as you said, it's nice to set a challenge for an experimentalist. So nice to make a prediction and say, hi guys, because it will, you know, obviously, as you said, you know, distinguish between the mechanisms. And finally, have you looked at silicon carbide? Is there anything known about that?
So this is we were looking at this is what we were doing. This thing was the silicon carbide
with no transition metal.
Oh, yeah, no, pure silicon carbide. Sorry, no, I haven't. I know there's been a lot more work done on silicon carbide as kind of, I think there was some catalytic studies for hydrogenation reactions, particularly hydrogen shuffling reactions. So that was another reason why we kind of decided to look at these transition metal silicon carbides. But no, I haven't modeled them myself, but there would be something very interesting if I could find a collaboration. They want some modeling on that, but yeah.
Great, thank you. I think that was a question really from Matt Davison. I hope I've represented your question reasonably well, Matt. There are some other questions in the chat, is particularly about your, I think it's not a drawing, I think it's some fairy lights on your wall, but that's from Matt. But I think, thank you very much again to Matt. We should move on. Thank you.
Okay. Thanks for listening.
And our next speaker